Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we're getting our third section in the conics section, which is the study of a cone sliced into different sections. So we've studied circles and parabolas in 9.1. We looked at in section 9.2 ellipses, which were the sums. And this video is about a hyperbola, which talks about the differences. And the hyperbola, usually we have to put two cones together. So if I have one cone up top and have a slice section, and then another cone down bottom and have its slice section, you can see the hyperbola. It comes from putting two cones together, top and bottom. So we have kind of two parabolas happening here. So again, we've got vertices on the major axis. We have a center, which we're going to define again as H and K, and we have a major axis, which again we'll call A, or the major axis is actually 2A, but the distance from the center HK to the vertice, oops, there's the vertice way out here, is A. This point is actually C, and we'll reserve that for college algebra. So again, all we're going to be worried about is not the foci points, which are here and here, which the function goes around the foci. We're just going to be interested in the center and the vertices, and then trying to determine whether it's a vertical or a horizontal. So here's where I was talking about putting two cones together. A little bit better picture diagram from the author than what I drew. So looking at the general equation centered about the origin, you want to try to determine whether it's a vertical or horizontal. So it's kind of easy. If the x term here is positive, then it's horizontal, and it's moving along the horizontal or x-axis. And if the first term is positive y, then it's a vertical. And the vertical one would look like this. It's going along the y-axis. So this one is actually, I've got H and K reversed here, because H always goes with the x value. So this is 3 units to the left if I was finding the center, 3 units to the left, and then 3 units up. So be careful, that's not always, the first number is not always x. In this case it's the y value, which is your up and down. This is your x value, which is left to right. So we'll talk more about how to determine what that is. Hyperbolas also have asymptotes, and either the equation of the asymptote is a over b or it's b over a, and students always get that mixed up, but it's always consistently rise over run. And if you just do your rise, there's your a distance, and then let your b distance be the other distance. So your a always goes to the vertice. So in this case, you can see this is your a distance going to your vertices, so your rise is your value here. So you can always kind of draw this little rectangle here. We'll call this b, so you can see that your rise over run for a horizontal is your b over a, because your b distance is your rise, and your a is your run. We're over here, if I draw that nice rectangle box, which the reason why I draw that rectangle is because that's where your vertices go through, as the corner edge of that rectangle. You can see that the rise is the a value, so that goes in the top, and the b, the run, is in the denominator. So it's always, I just always teach rise over run. Don't worry about if it's a over b or b over a. This is important too. A is always the positive number, so you always have to put a first. That way this is positive and a minus. It would be really tricky if they put the negative term first. They could, I suppose, they could say negative x squared plus the y squared equals the 1. That would also be a hyperbola, but that would be a trick if they wrote it that way. Negative 4 plus 5 is the same thing as 5 minus 4. We just usually write it as 5 minus 4 because it's one less positive or negative sign. So again, I have notes that I will be posting on the Blackboard, and you're certainly welcome to look at the notes. They are a little bit more in detail than what we're going to be going for this video, because they talk about how to find the equation, or excuse me, how to find the point, the foci, and we're not going to be talking about how to find the position of the foci, but the foci is what helps generate the hyperbola. But for this video, we're just looking at the asymptotes as either b over a, if they're, depending on whether it's horizontal, it could be a over b, but it's always plus or minus the asymptotes, because we've got a positive slope and we have a negative slope, and that's what's going to cause that nice rectangular box that we'll be drawing. So it's a little bit easier to look at an example of this. The a term always comes first, so a is 4 and b is 2, because remember, these terms are being squared, so all I have to do is take the square root of that. This is centered around the origin because there's no h and k, so all I'm going to do is go 4 units along the x, and there's a vertex, 1, 2, 3, 4 along the x, and this actually says 2 along the y. So 2 along the y would be here in red, but the red points are not actually points on the hyperbola, they're just corners of my rectangular boxes. So sometimes it's easiest to draw the hyperbola if you just get the corners of the boxes in first, or yeah, to draw in the corners of the boxes. So the line would look something like this here and this here for the corner of the boxes. And then once I have that drawn in, it's then a little bit easier to see. The hyperbola comes out this way and comes out this way then from the vertice. There's a little bit better picture of it, but you can see we just went 4 units to the right. Then you can name the equation. Oh, and if you wanted to, we could actually write the equation of the asymptote. Look at this. Here's your rise is 2 and your run is 4. So the equation of this line right here would be y is equal to 2/4 x, which of course you could reduce that to 1/2 x, and so that's what they're saying. Y is equal to positive 1/2 and y is equal to the negative 1/2 for this value over here. So equation of the asymptote. So let's try this again. Here a is equal to 4 and b equals 1, but I'm going to go 4 along the y-axis this time. So again, the center's at 0, 0 because there's no h and k value. 1, 2, 3, 4 up, and 1, 2, 3, 4 down. Now, instead of just trying to guess what that parabola looks like here, I'm going to go find the corners of my boxes again. So I'm actually just 1 unit to the right and 1 unit to the left. So there's my box, which is not actually part of the hyperbola, but it helps outline the hyperbola. So if I were to draw in the corner of these boxes, it's totally missed. Here and here, that will help define how wide the parabola is, and actually I wasn't that far off. So I got a vertical because the y value, the y term comes first, and again we've got the rise to be 4 and the run to be 1, so the asymptote is just 4 over 1, positive or negative. If they don't give it to you in standard graphing form, we need to collect like terms and complete the square. Remember, you can't complete the square with a leading coefficient, so I'll factor out a negative 1 from the x terms, giving me a positive 2x. Then I'll collect like terms here, the y's, and factor out a 4. So it's y squared minus 4y plus blank. And then I'm going to take this 11 and dump it on the other side. You don't have to do that, but it seems like that's most useful. Most students enjoy doing that. So the star step, which helps me complete the square, says take half of the middle term. So half of 2 is 2, and square it, we get a 1. But remember, it's not actually a 1 there. It's actually a negative 1 that I added to this side. And then I'll do the same thing over on this side. Half the middle term is 2. 2 squared is 4. So a 4 does go here, but 4 times 4 is 16. So that's a little tricky because students sometimes don't understand, why do you put a 4 here and a 16 here? That doesn't look like you're adding the same number. Well, remember, you're actually distributing a total weight on the left-hand side of the equation of 16. So if you add 16 to the left, you really should be adding 16 to the right. So over here we have negative 1, x plus 1, and if you're confused, I just use this number here, quantity squared, plus 4, just bring that down, y, just always use this sign, minus, always this number here, 2, quantity squared, equals, and I'll just add this up. And negative 12 plus 16 is 4. Remember, ellipses are not set equal to 4, they're actually set equal to 1, so I need to divide every term through by 4. So I'll leave this first term negative for a moment, but again, this is an interesting problem because I don't like the first term negative. These 4's cancel. Y minus 2 quantity squared over 1 equals 1. So I would really prefer you to swap this around. Y minus 2 quantity squared over 1 minus x plus 1 quantity squared over 4 equals 1. Remember, that's that if negative 4 plus 5, then I would write it as 5 minus 4 concept. But I like this to be positive because then I can see this really should be a vertical asymptote. So because the y term comes first, and a equals 1. A is not always the larger like in ellipses. Here's an example where a is the smaller, but it doesn't matter about larger and smaller. For hyperbolas, the rule is a is always first. For ellipses, the rule is a is always the larger. Different concepts, but again, all that's on my cheat sheets and the notes that I'll post on Blackboard. So I'm going to find the center here, and here's my h and here's my k. So the center, in this case, is going to be the opposite of this number, so negative 1, and then the opposite of this number, which is 2. So I'll find negative 1, 2, and then from that point, I'm going to go an a distance along the y-axis. So one value up and one value down is actually my vertex that I'll be drawing here. And then to find the corner of my boxes, I'll go 2 along the x from the center again, 2 to the right and 2 to the left. So that's going to help form my box. I'll draw in my asymptotes to help define how wide my parabola is. And finally, I'll draw in my parabola. Pretty wide looking, starting at the vertice on the y value. And then if I wanted to write the equation of the asymptote, I would say, well, the rise was 1 and the run was 2. So y is equal to 1/2. It's actually plus or minus x, but it wasn't centered at the origin, so I can't accept this. So it's actually y minus y is equal to the slope x minus x form. So I would say y minus the y value, which here's your x and here's your y, so y minus the 2 is equal to the slope, which is plus or minus 1/2 x plus 1. So I can't accept this because it's not at the origin. So y minus 2 and then equals 1/2. Yeah, it looks like it's the same thing right here. Here and here are the equation of the asymptotes, and it's centered about. One last thing about hyperbolas, which is kind of interesting. Not all hyperbolas come into that form. X squared minus y squared, or y squared minus x squared. This is also a hyperbola, but it's not a, here's a vertical one, here's a horizontal one. But this is going to be kind of oblique or slanted, and I just wanted to show you one quick example that could happen. If you see that, I would first of all solve for y, and then you could always just start plotting points, but I wanted you to know we've got a horizontal asymptote at 0 and 0 because there's no shifting here, but maybe the easiest way is just, if you let x be 2, then y would be 1, so there's a nice point. If you let x be negative 2, y would be negative 1, and then once you have that point, we could just start at that point and swoop toward the asymptote, and start at this point and swoop toward the asymptote. So if you wanted to find more accurately some more points, you could just go crazy and ask your calculator to find a t-chart. But there's that over 2 up 1, and then swoop towards these asymptotes here. Be careful, because they might not have the hyperbola at the origin, but hopefully they'll be nice to you starting out on My Math Lab. So again, there are applications for hyperbolas, such as a jet creating a sonic boom wave in the shape of a cone, and the intersection of this cone with the ground is a parabola. So just again to show you, there are some parabolic shapes also in science. We've got hyperbolic orbits. We also have elliptical orbits, but in this case we're talking about hyperbolic functions. So again, there are real-world applications for this. So if you have any questions, feel free to email me. Thank you.